So the Laplace-Beltrami operator. In this presentation, we're going to talk about this special way we can change the Laplace operator to work on more interesting surfaces. And I'll come to what that means later. And one important thing I'll mention before we start is that we're not going to be able to, at the end of this presentation, not going to be able to do computations. This presentation covers the context behind the Laplace-Beltrami operator, how it works intuitively. So before we actually start, we need to cover a pretty simple topic called a hypersurface. So if you just imagine a blob in space, and then you take the boundary of that blob, that is essentially a hypersurface. So more technically is you consider an open and bounded blob. So that means your blob doesn't run off to infinity, and its boundary isn't included, and we tend to call that E. And then we take the boundary of that blob and we call that sigma. And then the sigma, that is the hypersurface. So a particular example is we take a ball, so that's filled in the middle, a subset of R3, and that's what our E is. And then our hypersurface is the sphere. So like the crust of the ball or the boundary, or whatever you want to say. Okay. So we have like normal functions from like R2 in the sense that we take some point, for example, 1, 1, and we apply the function, we get some value 2. So here, the particular function we're running is x times y plus 1. So we take a point here, evaluate the function, we get a point on the real line, so -3. It's just a different way of drawing how the function works. Take points and they get mapped onto the real line. So this is great, and we can do a lot with this, but there are cooler functions out there with more interesting domains than R2 or R3. And for example, we could have the domain be a circle. So here we go, here's an example. You take a point on the circle and then you evaluate the function and you get -1. Take this point on the circle and you evaluate, you get 1. So I haven't actually explicitly defined how the function works here as I've done with the R2 example, but you can imagine defining some way to actually map the points on the circle to the real line. And if you can see here, the circle is a hypersurface. So we've taken a ball and then we've taken its boundary, and that's what the domain is for our function f. Okay, so you can see how functions were previously defined on these hypersurfaces, but now we're going to take a step further and talk about differential equations on these hypersurfaces. So normally when you solve a differential equation like y prime prime plus y equals 0, you end up getting a function y that takes a parameter x and you get some output. Now that y, this is a function from R to R. And so we solve our differential equation using maybe like the boundary conditions or whatever. And you use the fact that y is a function from the real line to the real line. And then you get some result. But what if we didn't want to solve the differential equation and get a function from R to R, and instead we wanted to solve the differential equation and say, get a function from the circle to R? This isn't just a pure math problem, like this is a real practical problem because engineers and physicists want to model, for example, how heat flows over interesting surfaces. So you take the heat equation, for example, and I don't know, we'll have like some surface we want the heat equation to be operating over, and then time as well. So we take a point on our surface, our interesting surface, for example, this donut or torus here. So take a point on the torus, and we want to know how the heat changes over time on this torus. So the heat equation would be a way we can model that behavior. But as of now, we haven't haven't discussed how you can actually do that with these more interesting surfaces. And as we've seen in class, a large focus of this unit has been on Laplace's equation, or more specifically the Laplace operator. So you can imagine having the Laplace operator on some function where you have the domain being one of these interesting hypersurfaces, and then mapping to the real line. Okay, so we have a technical problem before we can go much further, and that is that the previous slide here, I kind of slipped something underneath you, and that is these expressions or equations here are not well defined. And that's because the Laplace operator explicitly works on the n dimensions of your space. So for example, this donut here, it can be expressed with 2 dimensions because it's just the boundary of the torus. It's a 2-dimensional object. So for example, you could specify maybe the particular sort of like theta around the torus, and then a phi or something representing whereabouts on the circle around where you're pointing to. So this would be your theta, say, and then somewhere you would then indicate some point particular on the boundary of the torus using a different variable phi. Okay, so it's 2 variables which specify points on this surface, but so it's a 2-dimensional object embedded within 3D space. And so this Laplace operator works on the 3D space. It doesn't work on the 2D embedded object. So here we go. This is our function which takes a point on our more interesting surface, and it gives us a real number. And if we're looking at this expression, it isn't well defined. And that's because, as I said before, it works on functions in Rn, which is like the whole space we're working in. But our actual function that we're trying to find, this takes a point on our surface, our hypersurface, which is 1 dimension less. So for instance, the torus was just the boundary, so it's 1 dimension less. Here I've got an example with a circle. So you've got this 1-dimensional circle which could be specified by a single value theta, representing like how far around the circle you are, for example. And then we take a function which takes the theta as an argument and spits us out a real number. And the problem is that in 2 dimensions, which is where this circle is sitting, our Laplace operator looks like this. You take the second derivative with respect to the x-coordinate and the second derivative with respect to the y-coordinate. So we've got this 1-dimensional function and this operator which works on 2 dimensions. It's, we're gonna have some trouble because this is just doesn't make sense at all. Okay. So how do we solve this technical problem of having this dimension lower on our hypersurface? Well, it's actually a pretty engineering-y approach to solving the problem, I think. You sort of just take your hypersurface, which is 1 dimension less, and you just make it a bit fatter. You add some width to it. Now, what you actually do with this is then you can now say our function, which used to be from some point on this hypersurface, our function f, which takes a point on the hypersurface of the circle and then assigns it to a real number. Instead, what we do now is we define the extension of f, and I'll come to how you actually do that soon. But intuitively, you just take a point somewhere on this fattened area, and you draw a straight line to the closest point on the circle, and then you evaluate the function there, and then that will go to somewhere on the real line. So this point here is now associated with this value here. So our extended function is now operating on the domain is this fattened ring, and it takes to R. whereas our original function was from the one-dimensionless object, which was the circle. And the actual name for this fattened area is the neighborhood, and we denote it by this calligraphy N. So I did just say fatten the circle. There is a more rigorous way to define this neighborhood. And the way we do that is it's the union of all of the balls where their center is on our hypersurface. So the way we actually do that is we say we have a hypersurface, which is this circle, and then we look at every point on that circle, we draw a little circle around that, radius r, and then we do that for every point on the circle, and we take the union of all of these. So what we're going to get is we're going to get this like little band around our original circle. So that's how we do the fattening. So now I'm going to describe how we more rigorously define the extension, and it lines up very well with the intuition. So what we have is we start with a function f of x, which takes a point on our hypersurface. Then what we're going to do is we're going to define this projection operator. This projection operator is a special function which takes a point in a fattened area, and then it gives you a point on the hypersurface. So it's going to be a function from the neighborhood, so n, to our hypersurface, sigma. Then what we do is we take our point, which was in this fattened area, we project it down, and then we take that value and we evaluate it using our original function f. And it's really that simple. So it's the composition of two functions. First the projection and then our f. So that's the definition of the extension of f. Okay. So there are actually some edge cases or some bugs that come up when you're defining all of these things. If you're thinking hard enough, you could realize that this projection operator might not always work. So for example, in this circumstance here, we have a point x where there are multiple valid places it could be projected to, multiple like closest locations on this hypersurface. So how do we deal with that? Well, what we do is we basically say that the fatness is going to be determined by the fact that the projection must be unique. So this fatness is not legal in some sense. It needs to be skinnier. So we will define our like little r for our neighborhood to be smaller, so that now any point will be unique, as opposed to this situation where there is not one unique mapping. So yeah, here I've drawn it. There is another edge case though, where even if you can shrink your neighborhood around the hypersurface, you're still going to have points which map to multiple like projection points. This is a problem because we can't solve it by just simply shrinking the boundary here. So we basically say, sorry, you can't have these situations with sharp corners. As you can see, like you can get arbitrarily close, and you're still going to have two matching projections. So we just restrict our original like volume to being of class C3, and that ensures that we have sufficiently smooth boundaries, so we can always have a unique projection. So I've been saying the projection function. It makes sense what it does, but it's not very rigorous. So how can you know if you've got the right projection function? How do you know what you're doing is actually correct? So what we basically say is that our projection function is defined to be the function which satisfies this, and I'll explain each part of this in a moment. So for every point in our neighborhood, there exists a unique point on the hypersurface which is the projection of the point in the neighborhood onto the surface. So this is basically re-saying what I've been saying before, is that there's for every point in the neighborhood, there is a unique point that it gets projected to. And we can re-describe any point in the neighborhood as kind of being relative to its projection. So the point in the neighborhood X, what it is we take the unit normal vector from the place where X gets projected to, and then we got to scale it up by some amount. And that is the distance from the projection to X. So we get this normal vector, and I haven't explained how we get that yet. We get this normal vector, which is from the projection of X, and then we're going to scale it up a bit. And that's going to give us a vector that looks like this. Okay? And then importantly, we have to also add the projections that would like bring a vector up like here. So now we have a full vector that's pointing to X. So we get the projections that takes us to here, and then we add on this small vector which points from the projection to the place in the neighborhood. Now this distance function here, it's not just a distance function, because what if our point X was like back over here? Now our unit normal is still going to be pointing in like this direction. It's still going to be coming out this way, but we need our vector to point backwards. So our distance is actually a signed distance function, and so if our point X lies behind, then the distance is just negative. Okay, so I'm going to give like an explicit example of a projection function. So if our hypersurface is the unit ball, then our projection function is this function. So you take some point in space and then you normalize it essentially. So what that looks like is here's our circle, and maybe here's like the boundary of our fattened area, of our neighborhood. We take a point and essentially we rescale it so it goes onto the circle like that. Okay. And that's actually really all the theory we need to understand what the Laplace-Beltrami operator is, or more generally how we can do these operators on these lower dimensional functions. So the way we define the Laplace-Beltrami operator, which is this thing here, where we have the triangle for the Laplace operator and then this sigma for the hypersurface, we define that to be just the Laplace operator applied to the extension of f. And so if we remember from the previous slide, that extension is we project the point down and then we apply f. So it's a complicated idea, but if you think about it, what you're doing, you're taking these points, you're projecting them onto this lower dimensional hypersurface, and then you simply apply the Laplacian to the points in the neighborhood. So we've got some neighborhood, some n-dimensional space here, and our function is defined kind of like as these straight lines, where all of these straight lines get mapped to the same value because they will get projected to the same point. So all these points go to the same place on the real line over here. Like that. And so our Laplace operator can work on these points in this fattened region. And so that's what we do. And so that's really all there was time for in this presentation. There are far more things to talk about in the Laplace-Beltrami operator. So one important aspect which I didn't cover was how do we do gradients, how do we do vector fields, and the relationship between the Laplace operator and those, and taking the gradient and then taking the divergence. Those are well defined, and there's way more theory. It's very interesting to read about. So further areas you could look at is how the Laplace-Beltrami operator works with those. But yeah, So this is the Laplace-Beltrami operator. Thanks.